Welcome to the deep dive. Today, we're looking at something, well, truly fundamental. We're digging into the very nature of numbers, mathematical foundations. And our source material today comes from someone describing themselves as a serious scientist. They've got a background covering physics, engineering, maths, theoretical physics, quite the range, even involved in the Dutch history of MRI. And they kick things off with this really telling story from Delft University. A fellow student was given some measuring equipment, right? And the first thing the student does is completely take it apart, down to the bone.
Right. Just pulls it all apart.
Exactly. And why? Just to verify that you indeed would do as he was told. So this idea of really checking, questioning what you're given, that became a key lesson for our source. Now here's where it gets, let's say, controversial. The source argues we often don't do that in mathematics, specifically with Georg Cantor's work. They flat out say Cantor was wrong.
Wow. Okay, strong words.
Very strong. Calls it Cantor's nonsense, a fairy tale. Says it's inconsistent mathematics. Good for approximations, maybe, but we can never claim exactness. So, I mean, what does that do to our understanding of numbers?
Well, that's the big question, isn't it? And it's fascinating because it's applying that same rigorous, that take it apart idea you mentioned, applying it to the mathematical tools we use all the time.
Tools we usually just accept.
Exactly. The source points out, from when we're kids all the way through university, we're mostly taught to just accept the basics. These foundational things are treated as given, right? Let's just move on to more complex matters. Don't look too closely behind the curtain. So this source directly goes after Georg Cantor's work on natural and real numbers from the late 19th, early 20th century. Cantor's really famous work, like his diagonal argument.
Right, the one showing different sizes of infinity.
That's the one. That's what's being critiqued here. The claim is Cantor kind of started in the middle. He assumed you can always add one to any number and built these proofs on what the source calls improper definitions, or at least proper descriptions of the number systems.
Okay, so this is where it gets really interesting for me. The author says there's no proper definition of what a number is. Now, mathematicians might point to constructing numbers from set theory, the empty set and all that.
Yeah, the standard axiomatic approach.
But our source calls that foundation very shaky. So if number itself is shaky, where does that leave us?
It leaves us questioning quite a lot, actually. I mean, it forces us to think, are math frameworks universally true, or are they just human constructs, limited by how we perceive things? And this isn't just abstract theory, think about physics, AI, places where huge numbers, definitions of infinity, they actually matter. And to show how shaky it might be, the source asks this question. What happens when numbers get ridiculously large? I mean, impossibly large. They paint this picture. Imagine a finite number, but it has more digits, more ciphers than could fit in our entire galaxy if every tiny Planck-sized cube held just one digit.
Okay, that's hard to even imagine.
Exactly. The source says a number that big, it defies basic ideas. Identifiability, can you compare it, do arithmetic, can you even construct it? At that scale, the source claims you cannot always add one to a number. And if you can't do that, is it still a number? The source argues it is no longer a number, maybe just symbols. And this happens way before we even get to infinity.
So the implication is Cantor's arguments about infinity might be built on sand.
That's the conclusion drawn here, yeah. That Cantor's diagonal argument cannot be right because he is not talking of numbers. Not numbers in this rigorously defined, maybe limited sense. More broadly, it suggests we lack solid definitions for lots of things. Number, finiteness, infinity, continuity. Even the source points out, we don't really have a definition of definition itself.
Well,
kind of humbling, right? We're human, we have to live with limitations, even in how we define our most fundamental concepts.
So while Cantor's ideas, these different sizes of infinity, they can feel quite intuitive maybe. This deep dive suggests the very ground under them, what a number is, might be, much shakier than we usually think. It definitely makes you reconsider things we take for granted, even in fields like math that seem so exact.
Indeed. It really underscores the potential impact of assumptions we don't examine closely enough, even the most basic ones.
So maybe for you, listening right now, think about this. What bedrock ideas in your own field or just your own understanding of the world do you kind of trust implicitly? And what might happen if you decided to really disassemble the measuring apparatus and check them out for yourself? Some food for thought there.